Hello and welcome to another installment of our thermodynamics video series. Today we are going to switch types of systems from what we've been doing in the last few weeks. We've been talking a lot about power cycles. This is our first foray into something else than a power cycle, namely the refrigeration cycle. And as we'll see in a moment, the main feature is that instead of going clockwise on a TS diagram, refrigeration cycles go counterclockwise, meaning that they require an input of energy to perform an entire cycle. As part of this first video on refrigeration, we'll introduce the concept really of refrigeration. I just did. It's a system that goes counterclockwise, produces a refrigerating effect, meaning that it pulls heat from a cold reservoir and dumps it into a hot reservoir, which according to the second law of thermodynamics requires that work be expended to do. We'll introduce the main performance parameter for refrigeration cycle, which is the coefficient of performance, beta. I'll also briefly talk about the equivalent for a heat pump. And I'll introduce the gold standard cycle that represents the best case scenario for refrigeration cycle, and you may have expected that would be Carnot. Finally, I'll talk about the most prevalent type of refrigeration cycles out there, the one that's being used in your AC system in your car, for example, your refrigerator, your freezer, and many industrial applications, and that is the simple vapor compression refrigeration cycle, which your book calls the SVCRC, but which the HVAC and our industry typically simply abbreviates as SVCC for simple vapor compression cycle. All right, let's get started. So the performance parameter that characterizes the refrigeration cycle is beta, called the coefficient of performance. And beta is defined as the useful refrigerating effect. So as a typical performance parameter, it's what I want over what I pay for. And what I want here is useful refrigeration effect. And what I'm paying for is the net work in to the system. Actually, let's just spell it out and then we'll simplify it afterwards. Net work in cycle. So we'll call that Q in over work in net, and this would be Q in useful. And if we apply L'Hopital's rule again to numerator and denominator, we are going to get the same expression on a rate basis, which is how we are usually going to be using this in practice. So it's the rate at which heat is being transferred from the from the cold reservoir divided by the power of that needs to be added to the cycle, the rate of energy input into the cycle in order to accomplish that. And so that is, of course, Q dot in use over the total work in minus whatever work out that we're able to recover if we could. Frankly, in practice, this guy here is going to be negligible in practice. Okay, so that's it. That's the definition of coefficient of performance beta. Let's highlight that and call that equation 1. We're going to immediately put it to the test here. Change color, make that pretty. Call that equation 1. Voila. All right. I should also, while I'm at it, highlight versus the heat pump coefficient of performance, COP. Yeah, that's right. The coefficient of performance is often simply referred to as COP, the acronym. So you'll see this a lot, especially if you stick with HVAC. So the heat pump COP is very similar in definition to beta. The heat pump a heat pump is different from a refrigerator in that what we are trying to do here is heat up the hot reservoir by extracting heat from a cold reservoir. So if you will, we're on the opposite end of the spectrum, if you will, of our two reservoirs. But as you can imagine, the method with which we use it or quantify it are going to be very similar. So gamma, which is the symbol for the heat pump coefficient of performance, COP, is defined as Q dot out total. This is the heat that's being dumped to the hot reservoir, divided by the same denominator, what I'm paying for, which is going to be the net work in. Okay, again, there's usually no work out that can recover the amount of work I'm putting in, but that's another story. All right, here we are. Let's call that equation 2 to formalize gamma here. Equation 2. All right, so we've got two coefficients of performance, beta and gamma. Let's start talking a little bit about the ideal, the granddaddy of all these cycles, and that is going to be the Carnot Refrigeration Cycle. Very similar to what you're used to from power systems, except that now we're going counterclockwise, and we are going to add heat. Sorry, add work to the system. So Carnot Refrigeration Cycle, bracket, the gold standard. This is the Lemieux expression here for Carnot cycle. The gold standard of all cycle from Mr. Carnot himself, Sadi Carnot. Great, very interesting life here. If you get your hand on his biography, it's a fascinating person. One of the giants of science, a very young person. He died young, but he did a lot in his short life. All right, so that looks a lot like what you're used to for the Carnot power cycle, right? Except as you've noticed right away, we are going counterclockwise on the TS diagram, and that's your first important clue that something very different from a power cycle is taking place. So what we're going to do here is calculate the coefficient of performance for this particular cycle, beta for this particular cycle, and that therefore is going to establish the gold standard for all the other cycles that we're going to analyze afterwards. It's going to be the gold standard because just like in the power cycle case, every process that makes up the cycle is reversible, okay? Meaning that there is no irreversibility. So if you're looking at it from an exergy standpoint, the sigma term is zero everywhere. The only change in entropy that takes place is the change in entropy that's associated with heat transfer. And so that's what makes it the most efficient possible cycle as possible. So let's describe it formally. I'm not going to write down each step here. I'll spell them out for you instead. And then we will use the representation on TS diagram to figure out what this COP is. So step number one is an isentropic compression. So that's going to be this guy right there. Okay, there we go. That's the compressor. So the compressor takes a refrigerant that is going to be nominally, well, in the case of this particular system here, a saturated. It has some liquid and some vapor, and it compresses it until its quality is exactly 1, and it does so reversibly. Once again, that's process number 1. So it's an ideal compressor. Isentropic efficiency of the compressor is 100%. And at the outlet of the compressor, I have a saturated vapor at a higher pressure and a higher temperature. but this saturated vapor has a quality of 1. So I'm going to end up right there on the edge of the dome at the outlet of the compressor. Then that saturated vapor is going to condense, meaning it's going to experience a phase change in this one representation of the ideal Carnot cycle. It's going to experience a phase change during which it's going to dump reversibly heat into our hot reservoir, which is at T sub H. So as it does that, as it dumps heat into the hot reservoir, that means that the condenser temperature must be at the same temperature as the warm reservoir. That's the only way you can have reversible heat transfer, is if you only have an infinitesimal temperature difference with the body with which you're exchanging heat. That's what's going on here. So the condenser and the hot reservoir are at the same temperature, and that's what we're seeing here on the TS diagram. Okay. So that is step number 2, also reversible heat exchange. We come out of the condenser at state 3 as a saturated liquid, quality 0, at that same pressure as came out of the compressor. So loss-free flow through the condenser. There's no delta P in there. Next, we enter a turbine at state 3 as a saturated liquid, and we expand, go from pressure at 3, which is a high pressure point, hot reservoir temperature point, down to the low pressure point, low temperature reservoir point, corresponding to the saturation pressure at T sub C. That's the pressure that we're going to expand through the turbine to. And so therefore we're going to get some work out of that system at that point. So this is work out, and this here is work in. And the difference between those two work is the net work in, the denominator on our beta, just to keep things in perspective. Finally, we get into the evaporator as a saturated liquid vapor mixture of some quality, neither 1 nor 0, and then we're going to evaporate that as we flow through the evaporator by sucking heat from the cold reservoir at T sub C reversibly, meaning that the evaporator itself is also at that same temperature, for the same argument that the hot reservoir temperature heat transfer was at the same temperature. Until we close the cycle and end up at state 1, which is our inlet to the compressor. All right, does that make all sense? Makes sense, I hope so. Let's calculate the coefficient of performance then for this particular cycle. Coefficient of performance, calculate COP for Carnot cycle. So, as we said above, equation 1, beta is equal to Q in divided by work in net. And if we're looking at the entire cycle from the first law, work in net is going to be the work in total minus work out total. And our statement of the first law, we'll spell it out over here, states that for any process or series of process that runs through, the change in in stored energy must be equal to the total heat in. And notice here I'm doing the exercise on a per energy basis. Okay, so I'm looking at the actual energy, joules. Throughout the cycle, I could repeat the entire thing based on a rate basis, but I'm going to do it this way. Q in minus work out. I've seen this before, and these are net values, right? So let's make that clear here. And since we are running in a cycle, all the properties must return to their original point. So therefore, the stored energy, which itself is a property, must be must return to its original state. The thermal energy, kinetic energy, and potential energy, which typically on a cycle like this would be negligible, but the thermal energy certainly isn't. That would be U. Comes back to its original point, so therefore delta E is equal to 0. And so that means that that's equal to Q in net minus work out net. And so that means that Q in net is equal to work out net. And that means that work out total minus work in total, right? That's my workout net must be equal to Q in, let's see, I'm sorry, Q, that's going to be, mess this up here. Yeah, no, that's correct. Q in total minus Q out total. There we go. Yeah. So the net workout is equal to the net heat in is what we're saying, and that's what we wrote down there. And so slap a minus sign on that on both sides, and I'm going to have the expression that I need for the denominator of my coefficient performance, and that's what I was getting at. So I get a bunch of heat balance as opposed to having to deal with that work. So Q out minus Q in. Okay, so I'm going to drop the total the total subscript here. I'm clearly I'm dealing with all the heat that's being transferred over the entire cycle, whether it's in or out. All right, that's what we got. So what is the heat in and the heat out for the Carnot cycle? This is what we have to deal with now to substitute to find the coefficient of performance. So recall from the second law now, TDS is greater than or equal to the heat transfer that occurs to cause the change in entropy. And in the limiting case of a reversible process, then that inequality turns to an equality. And in the case of heat transfer, what that means is that the heat transfer takes place at constant temperature across a body where there's no temperature difference, or infinitesimally small temperature difference. That's what a reversible heat transfer process looks like. Okay, so we'll apply this to the Q in process and the Q out process, which is the condenser, so the evaporator and the condenser, one after the other. So for the case of the Q in, which is the evaporator, for the evaporator, Q in, that's where Q in takes place, must be equal to the integral from state 4 to state 1, which is where the heat transfer from the cold reservoir takes place, of dq. All right, that's going to be my Q in, and that's going to be equal to the left-hand side of the second law expression from 4 to 1 of TDS. And since for that part of the process the temperature is constant at T sub C, then what that means is that I can take it out of the integral. So I've got T sub C times the integral from 4 to 1 of ds, which of course is just S1 minus S4. It's a dead easy integral, right? So really what we're saying is that the heat in going into the refrigerant is this area right there underneath the curve. But you already knew that, right? So let's repeat it for the condenser for Q out, and I bet you that you can get the result. Oops, for condenser. Q out is going to be the integral now from 2 to 3 of Q. It's actually going to be minus that integral, right? Because we are now taking the heat out of the system as opposed to adding heat into the system. This is Q into the system here. And so, therefore, without doing all the math here, I think it's fairly straightforward from what we just did. This is going to be equal to TH times minus delta S, which is going to be S2 minus S3. And notice here that because both the compressor and the turbine are isentropic, the entropy at 2 is the same as the entropy at 1, and the entropy at 3 is the same as the entropy at 4, like we mentioned earlier. And so therefore that means that what I got here is T sub H times S1 minus S4, right? And that's going to be important here for a calculation of beta, because all those S are going to cancel. So substituting that into beta, we've got beta is equal to Q in divided by Q out minus Q in. Q in divided by Q out minus Q in. That's going to be equal to T sub C times S1 minus S4 divided by T sub H S1 minus S4 minus T sub C S1 minus S4, which is equal to T sub C divided by T sub H minus T sub C. That's the COP of a refrigerator. Equation 3. Of the ideal Carnot cycle. So that's worth thinking about for a little bit here. Some reflection / observations on this here. Observation on this result. Observation on COP. Because while we're not going to run refrigerators exactly on the Carnot cycle, they're going to aim to approach the coefficient of performance of the Carnot cycle, and that tells us some indication of what makes the cycle as efficient as possible. So the first thing that we see for maximum COP, maximize COP, is that we want T sub C as high as possible. And I guess from an engineering intuition standpoint, that kind of makes sense, right? The hotter the cold reservoir it is that we're trying to cool down, the hotter it is, the easier it's going to be. So it's going to be not that hard to make a machine that can do that job fairly well. The second observation, perhaps a little bit less obvious, is that we want the cold and the hot reservoir to be as close to each other as possible. We want T sub H and T sub C to be as close together as possible. And this is a bit surprising to us coming from our analysis of the Carnot power cycle, because in the Carnot power cycle, that was exactly the opposite, right? We wanted the two reservoirs, the hot and the cold reservoir, to be as far from each other as possible for maximum thermal efficiency. But beta is not an efficiency parameter. It's a coefficient of performance. It's not the same. And the reason it's not an efficiency is really our point number 3 here. Let's put numbers on these things here because they're worth making a tablet for Mount Sinai with. The third point is that the COP can be greater than 1. It's 100%. And this is surprising to us a lot, because every time we've talked about these thermal efficiency, there is no way the thermal efficiency could ever beat 100%. Well, the coefficient of performance routinely beats 100%. So for most devices, actually, even the actual AC unit inside your car, coefficient of performance is going to be in the 4-5 range. So 400%, 500%, meaning that the amount of heat that you can suck out of the refrigerated space, the rate at which you're sucking it out is a lot higher than the work that you're putting in. It doesn't mean that the amount of work that you're putting in is insignificant, but it means that you got some sort of a lever here acting on your side. So that is kind of a really, really good feature. So those are the 3 basic laws or observations that we can make for the COP based on watching the Carnot cycle. I'm not going to go through the same derivation. I'll leave it as an exercise and for you to do here. But I will ask you to see if you can show this exercise. Show that the maximum heat pump COP is gamma is equal to T sub H over T sub H minus T sub C. All right, see if you can show that. And that's when we operate the system as a heat pump, meaning that our goal is to heat up the hot space here. This is what we're trying to do. So you've seen those heat pumps. They're above ground machines that are on the side of houses, and basically what they're doing in the middle of the winter is sucking heat out of the cold atmosphere outside. That would be the cold atmosphere, cold over here, and dumping it into the house, which would be over here. So that's how a heat pump works, and the maximum efficiency that you can get out of that, or not efficiency, but coefficient of performance that you can get out of that, is given by this gamma value over here. All right, so you have all the tools here that you need to do this. Now, how do these cycles differ from the real refrigerator? And here I've got some pictures of real refrigerator here to try and highlight this for you a little bit. Particularly like this guy right here, because I think it highlights the true components most faithfully. Here's the compressor, which is the starting point of our system from before, right? That's what separates state 1 from state 2. That would be state 1 right there, and that would be state 2 right there, going by the diagram that we set up before, TS diagram that we did before. And the refrigerant is then pushed down up this tube, I should say, all the way down to this grade right there. Oops. Right here. Yeah, oops, I got this wrong here. All right, start over again. I don't know why people make these diagrams in a way that doesn't match the TS diagram and go counterclockwise. People just don't like to go counterclockwise. So we are going to go like this at all here. Yeah, okay, that's the evaporator, right? Okay, 1 to 2. This is the direction in which the compressor is going, and coming out of the compressor is our hot refrigerant, and the hot refrigerant is going to go through a series of coils that are typically behind the fridge, and that's what these guys are right here. These are the condenser coils, and so the purpose of these coils is to cool down the refrigerator. It's very hot compared to the room, and so it's dumping heat into the room, and that's what we've got on this diagram right here. On the back of the fridge, these fins are dumping heat to the room, to the atmosphere of the room, so that's our Q dot out. And similarly on this side here, that's our Q dot out. Up until the refrigerant is essentially a saturated liquid, which is going to happen once we reach this transition point right there. Now, if you recall in the Carnot cycle diagram, let's go back up here and look at it quickly. At that point, this is the point at which we're at here, point 3. We'd be going through a turbine to expand the refrigerant down to the low pressure, low temperature point and extract some work out of that. It turns out that the amount of work that you can get out of a turbine at that point is rather small. And so in practice, given that a turbine is actually very expensive and that they don't work too well when you've got a saturated liquid going through them, real life refrigerators don't do that. Instead, what you see is this tiny little tube, and this is why I like this picture, because this is the setup that you're most likely to see every day on your actual refrigerator. This little tube right there is a capillary tube. It's basically a tube that's there to provide friction. Think of it as a throttling valve, if you will, which is all friction. And the point of that is to drop the pressure. And since you're starting out with a saturated liquid, you're actually cooling the fluid down significantly in the process, even though it's a little counterintuitive, given that you're flowing through a tube with friction. But by the time you come out of that, you're at state number 4, which was the inlet to our evaporator on the Carnot cycle. Right, we're at that point right there after we go through the capillary tube. And now we're ready to do our cooling effect. So our cooling effect is going to go through this guy right here, which is likely your freezer compartment if you have an old style fridge or a dorm-like fridge. They're still kind of made up like this. They look like this. And this is where all the heat gets sucked out of the inside cavity of the fridge. And the inside cavity of the fridge is what's at T sub C. And once it gets to the other side of the evaporator, the pan that makes up the bottom of your freezer section, of course this entire pan is roughly at the same temperature because it's a saturated liquid vapor mixture. But once we get out of it on the other side, then we pretty much have a saturated vapor, maybe even slightly superheated vapor. And we're ready to repeat the process at that point. That would be, we're almost at state 1, really over there. But what we're going to do here is one last hurrah for the refrigerant before it goes to the inlet of the compressor in this real life scenario here, and that is to cool down the capillary tube a little bit more and recover some of that, some of that cold, if you will, or low temperature sink to drop the temperature of the capillary tube even more. Okay, and this is in contrast to this second diagram, where instead of having the capillary tube, there's an expansion valve or a throttling valve or a plug, if you will. It does the same thing as the capillary tube. It just does it in a much more reduced volume. And obviously you can't weave it around the return tube of the evaporator section, so you can't dump heat from the evaporator tube, the return evaporator tube, quite as easily. So let's take a look at this on the TS diagram. Couple of main differences with Carnot to highlight here. The first one we've talked about, and that is that expansion valve / capillary tube. If you recall from your analysis, and you should be able to prove this using Reynolds transport theorem here, as I'm flowing through an expansion valve, a throttling valve, then the first law boils down to the fact that the process must occur at constant enthalpy at steady state because there is no work done. And in the idealization, there is no heat being transferred out of this expansion valve. So Q out is equal to 0, and work out is also equal to 0. And so if we're at steady state or unsteady term, and RTT goes away, and all we're left with is the convective term on RTT. And since the mass flow rate going in is the same as the mass flow rate going out, it boils down to H3 equals H4. That's the effect of a throttling valve. So let's, I did this very quickly here by words, but you should be able to do this mathematically yourself, I think, without too much trouble. And so while the enthalpy is constant between 3 and 4 over here, enthalpy constant, H3 equals H4, what is absolutely clear for a throttling process like that, which is really lossy, a lot of friction, is that S3 is definitely not equal to S4. S3 is not equal to S4, and that's why 4 moves to the right there on the TS diagram. And so that's kind of a bad thing, right, for us, because we lose this potential refrigerating effect there. We can't do anything with that. So now the refrigerating effect is going to start here and end there, and this is going to be the only Q in we're going to be able to get here. That's Q in, the new Q in, compared to Carnot, which started all the way on the left right there. So bummer. The second thing that we notice is the fact that we do not like compressors that are working in the saturated region, right? It's not an efficient process to pump a liquid, or not a liquid, but a saturated mixture in any way, whether it's with a positive displacement pump or anything else. Machines don't like this mixture of vapor and liquid. Great with pure liquid, great with pure vapor, not good with a combination of both. So the solution in the fridge case is to move everything to the superheated region. And in the idealized representation of this, we're going to start with an inlet to the compressor that's a saturated vapor at 1. Okay? So if we're starting with a saturated vapor, and in the ideal case, we're compressing it isentropically, then we're going to end up with a superheated vapor at 2 ideal. Again, in real life, what you are going to expect for a real fridge is we're going to stick on this isobar right there, and the compressor is going to actually have an isentropic efficiency, and so we're going to be here at 2 actual. Okay, 2 actual means that the outlet of the compressor is hotter than the best case scenario that we could have over there, which means that our condenser is going to have to work that much harder, right? So now this is the amount of heat that I'm dumping into the room. Okay, so quite a bit more than before, unfortunately. And that makes my denominator, right, which was Q out minus Q in on my beta, a lot bigger than it was for the Carnot cycle. And so therefore my beta just took a hit. So clearly the coefficient of performance of a standard or simple vapor compression refrigeration cycle, which is what this is, simple vapor compression. I'm going to put refrigeration here because your book likes to talk about that, but the HVAC industry simply abbreviates it as SVCC. Therefore, that cycle, beta of SVCC, is less than beta of Carnot, but you've already expected that, right? Carnot being the gold standard. So that's it. That's the coefficient of performance of that guy. And I'll leave it as an exercise, not too tough. You guys, Cal Poly material exercise. I don't want to insult you by deriving everything from scratch for you. Show that beta for the SVCC is equal to H1 minus H4 divided by H2 minus H1. Okay, and what I'm saying is that that is less than Tc divided by T sub H minus T sub C. Okay, so that's pretty much it for us for today. I think this is kind of a good place here to start. Oh, I should probably highlight a little bit. Let's go back to this compressor here and make that one point a little bit clear as well. I'm going to erase all that stuff here. I don't need this anymore. I want to highlight the isentropic efficiency of the refrigeration compressor, which is also an important parameter. And it's denoted the exact same way as we do for gas turbine or for a pump on a Rankine cycle, and that is going to be the delta H, let's see, ideal divided by the delta H actual, which here is going to be H2S minus H1 divided by H2 actual minus H1. So that's the isentropic efficiency of the compressor, and of course that's a number that's always less than 1. Okay, I think this does it for this lecture, this introduction on the refrigeration cycles, both the SVCC and Carnot cycle. Hope you've enjoyed the presentation. Take care and have a good rest of your day.